Awesome. All right. So yeah, I'll be prattling along on circular economies and lithium-ion batteries for the next 5 minutes. So here we go. So before I get into what I do, I'll just give a brief about why I do it. So we all have mobile phones, laptops, AirPods, all these portable electronics, as well as we are seeing an uptick in the number of electric vehicles on our roads. And there is a common factor among all of these. These are all powered by lithium-ion batteries. And as expected, as the years go by, the demand for these batteries are going to skyrocket, and there's going to come a point in time where the demand outpaces the supply. And this is going to lead to a host of logistical problems. And my research focuses on circumventing this issue. And we are trying to do it by creating a circular economy model for lithium-ion batteries. So what do I mean by that? So essentially, to supplement the supply chain from apart from primary extraction from mining, we employ techniques such as recycling, reuse, refurbishment, recovery, regeneration, all the re's that you can think of, and try to keep the raw materials in the manufacturing loop for as long as possible, and also to minimize waste and pollution to keep in touch with sustainability goals. So essentially, that's the crux of my research. And this is a typical circular economy model for lithium-ion batteries. We're taking EVs, electric vehicles, as the example here. So how it works is that once a battery goes below 80% capacity, it cannot be used in an electric vehicle anymore. But that does not mean it's completely obsolete. It still has some juice left in it. So it's taken in, repurposed for a second use application that does not require as much capacity, and there it runs its course. And once it's done, it's taken in again, processed and recycled and reintroduced into the energy stream to be used for the second generation of batteries. That's how a typical circular economy for lithium-ion batteries would function. So there's essentially three strategies to achieve this recycling or regeneration step. The first two might be familiar to most folks. These are very common strategies, especially in mineral processing, pyrometallurgy and hydrometallurgy. We're using the same concepts in metallurgical operations and kind of extrapolating and repurposing that for recycling. So pyrometallurgy is an established technique in this area. However, it's very energy intensive and there's a concerted effort to wean away from it. So most of the research is focused on hydrometallurgical or direct regeneration techniques, and so is my research. So hydrometallurgy essentially uses a combination of chemicals to extract the metals or the components in a battery and reuse it for the next generation of batteries. And my research focuses on optimizing this established technique. The third one is direct regeneration, and this is quite interesting. It's still a nascent technology, it's still in the lab scale. Essentially, the concept is that the active materials in the battery are taken out and they are regenerated without destroying its structure. So it can be used directly for the next generation of batteries. So the hydrometallurgical part of my research involves this process flow. So I essentially take a used commercial battery, kind of unfurl it and take out the active material in the cathode. I subject it to an acid leaching step using a combination of chemicals. And finally, the metals are dissolved in that solution and I precipitate it using salts to be used for the next generation of batteries. So this is an established technique. My contribution here is the chemical mixture that I'm using. And the goal is to make it more environmentally friendly. And using my current methodology, I'm able to achieve around 80% metal recovery. And I'm sure as the trials progress, that number is going to rise proportionally. And towards the direct regeneration part of my research, so essentially in a battery, the reason its performance decays over time is that a lithium ion shuttles from the cathode to the anode, or from the positive to the negative. That's essentially the principle of a battery. And sometimes it gets kind of stuck in the anode and doesn't shuttle back when you're trying to charge it. So this loss of active lithium is one of the reasons for a capacity fade or capacity decay in a battery. So this aspect of my research involves using lithium salts to kind of fill the holes or fill the areas where the lithium is lost and kind of regenerate it directly to be used for the next generation of batteries. I've had some success with this method. I was able to restore around 60% capacity, and I'm sure as the trials progress, I'll be able to get better results using this novel technique. And finally, this is in terms of the cathode, this is something interesting that my lab has recently started working on. So say a battery has an initial capacity of say 150 units, And usually when you recycle it, the final product will have something similar. We introduce a certain extra steps into it, and the recycled battery has a higher capacity, say from 150 units to around 200 units in its final form. So this means that we are recycling with an upgradation, and it's called upcycling. And this is something really interesting that my lab is currently working on. This is the typical process flow of how an upcycling operation would work. And finally, let's not forget about the anode, the negative side. Typically, the compound used is graphite. And as I mentioned earlier, during the cycling process, some of the metal gets stuck in the graphite, leading to its degradation. So a regeneration or recycling operation in this end focuses on kind of removing the metal as well as repairing its structure. And the metal is removed by using an acid leaching steps, using acids to dissolve the metal. And finally, a high temperature process is introduced to kind of repair the structure and get it back to battery grade. Uh, so yeah, thank you for listening. That's essentially the crux of my research. I'm open to any questions.